Alright, 8.4, day number 1, exponential models. Class opener is to complete all these derivatives and then the respective integrals. Just a note here, these two can be solved using u substitution. Write them in terms of sine and cosine and you should be alright. You probably won't see them on an exam, but it's good to be aware of. Alright, so the rate of increase in population during a short period of time is directly proportional to the size of the population at the beginning of the period. This can be modeled with a differential equation. What is a differential equation? It's an equation which involves derivatives whose solution is a function. So the differential equation with p equal to population and t equal to time. So let's look at this. The change in population with respect to time is some constant times that population. Find the solution to this differential equation. What is a differential equation? Alright, so here we go. We've got dp dt. So dp dt equals kp times dt, right? Now the next thing that I would do is I get that p on the same side as the dp, so I'd divide both sides by p or multiply by 1 over p. That would cancel them here and bring it on over here. So I get 1 over p dp is equal to k times dt. So integrate, I've separated, now I'm going to integrate. I get the natural log of p is equal to k times t plus c. Right. So if I want to solve for p, I would take e to the power of kt plus c. Using properties of exponents, that would be e to the kt times e to the c. Alright, at this point I can drop the absolute values because population is positive. We're not worried about a negative population. And the next thing that I would do is I'd let e to the c, right, equal our initial population. So our population would be e to the kt times our initial population. We'll just rewrite that. So the solution to this particular general differential equation would be initial population times e to the kt, where k is the whatever this constant is and t is in time. Alright, so we showed that this was true, right? Now if we want to talk half-life, we're going to replace p with half of p0. So that's half of our original population. So we would just simply rewrite and substitute in 1/2 of p0 equals p0 times e to the kt. And what we want to do is we want to solve for time, or t, right? Because that would tell us how long it's going to take for our population to be cut in half. So we would divide both sides by p0. So we get 1/2 equals e to the kt. Then I would take the natural log of both sides. When you take the natural log of the right side, it allows you to bring that kt down in front using properties of logarithms. And the natural log of e is 1. Therefore, we get the natural log of 1/2 is equal to k times t. Okay, therefore, t would be equal to the natural log of 1/2 over k. And therefore, what we could do is if we wanted to rewrite that, it's possible to rewrite it as the natural log of 1 minus the natural log of 2 over k, but not necessary. In some cases you might see it in that form, However, I would say this is your primary form. So this is useful because you will be given something like this on the exam, right? You'll be given this formula, and you can solve for t regardless of what your value for k is and what your population is initially by taking the natural log of 2 over k. I'm sorry, I meant natural log of 1/2 over whatever that value is. And that would be a quick way. Like if they say the population is 10,000, here is the rate, which would be k, right? And when would, according to this, when would the population decrease by 1/2? You could easily plug into this and make a quick calculation. So for your homework on exponential growth and decay, you must use formula 2 directly. Formula 2 being this one here. And this will be on the exam. You must be able to solve any differential equation that you're given. So, all right, that's it for 8.4, day number 1 on exponential models.